So there's a third lecture, which I'll advertise in a second, but at least for today, over the course of 2 lectures, giving some kind of introduction to astrophysical plasma physics. This includes both situations where you can treat the system like a fluid, which will be this lecture, and then the next lecture after that will be systems where you can't, be careful out there, situations where you can't treat the system as a fluid. And so that'll be mainly kinetics. So what I've done, I believe it's being posted, right? I've got a giant set of notes. I'm not going to go through all these. You can find them. I've also put them at my website here. I believe Sasha's posting them to the AstroSoma website. The idea here is that I have a fixed amount of time. MHD and kinetics is a vast subject. And you're all at different levels, so I've been told. I've been told to assume nothing about your background. So as a result, there's some of you in here who know some of the stuff that I'm going to say already. There's some of you who might not. As a result, what I've done is tried to put together a self-contained set of notes that has something for everybody. So there's some basic things that I'll talk about today. There's some more advanced topics which are done in the notes. I obviously can't do derivations at the board. I've been told that I have, small windows to work with on the board, so I'm not going to do derivations so much. But for your edification, all these derivations are in the notes, so you actually have something to take with you. And any sort of details that might come up when I'm speaking that you might be confused about, please interrupt and ask. But in all likelihood, you'll find your answers in the notes. Accompanying these notes are 2 problem sets, which are just for your benefit. They're optional. I don't expect you to do them. They're quite long, so they're not even expected that you would do them in a week. But the idea, again, is that this is a short summer school. I'm giving 3 lectures on all of MHD and kinetics, apparently, in a short amount of time. So the problem sets are yet another thing that you can take with you, right? And you'll find in these problem sets problems that are fairly straightforward, which are just trying to hammer home some basics of MHD and kinetics. And then there's some problems which are really quite advanced, which are indicated that they're advanced, and there's even some that take quite a lot of work to do. But the point here is that you're all at different levels, so hopefully there's something for everybody in there. And even if you're not prepared for it just now, maybe in a year you will be, and you can reference back to these notes as a reference and maybe check out these problem sets to learn additional things. I should say the way the problem sets are set up, they're not an assessment, right? So they're written in a completely pedagogical way, which is these are topics that aren't in the lectures and that aren't in the lecture notes. So I don't just give you a question and say, work this out. It actually leads you through the problem so that you can learn something from doing the problem. But they're all special topics which are related to what I'm going to talk about, but they're not an assessment to see whether you understood it. It's an additional bits of information framed in a way that just takes you through the process of solving these problems. So I hope you find them useful. Right, so to get started, please don't lie. I need an accurate count. Who knows MHD? I should have said who thinks they know MHD. Okay, good. I'm going to say some things at the beginning which might be boring for you, but it's always nice. I always find it nice to hear things multiple times in multiple ways. So if you just find the first half hour or so boring, just sit tight. Take a look at the notes and try find something challenging, work on the problem sets or something. But for those of you who don't know MHD, hopefully this will be fairly self-contained. And of course, please interrupt. I want this to be interactive. I'll ask you some questions, so don't worry about it. It's not supposed to be just me talking, because that will get really old really fast, since I'm doing this 3 times. Good. So I thought I would just start with a simple question. What is a plasma? That's actually not an easy question. There's, if you go on Wikipedia or whatever, there's this textbook definition. It's sufficiently ionized plasma. Plasma is a sufficiently ionized gas that displays collective behavior. And you could argue with each of these aspects. So sufficiently ionized, you have to decide what does sufficiently ionized mean. Stars form in molecular clouds which have temperatures of 10 Kelvin and degrees of ionization 10 to the minus 7, 10 to the minus 8. So for each neutral hydrogen, well, for each electron, there's 10 to the 7 neutral hydrogen molecule, or molecular hydrogen, neutral molecular hydrogen sitting around. From that standpoint, you think, all right, this is just the hydrodynamic fluid. But you actually have to define what you mean by sufficiently ionized. In this case, it is sufficiently ionized for you to worry about magnetic field effects, even though its degree of ionization is 10 to the minus 7 or 10 to the minus 8. And the reason for that is the time scales involved, right? So if you pose a question whether something is sufficient or not, you also have to write down some length scales and time scales and compare these length scales and time scales to inform you relative to everything else what is important. So I thought I would start the lecture just by giving you, running down some systems of interest to me, and giving you some information about these systems, and sort of cataloging the relevant length scales, the relevant time scales. What does this say about whether we can treat it as a plasma? What does this say about whether we could treat it as an MHD plasma? And that'll inform the remaining lectures. I don't know, if you flip through the program and you see my lecture titles, you'll know that this lecture is going to close with me talking about MHD, but then saying it's not really good enough for any of the systems on the board except for maybe the ISM, and only certain phases of the interstellar medium. And that'll segue into the second lecture by Phil on non-ideal effects that manifest in protoplanetary disks and protostellar environments. Great. So that's the plan. So on the board over here, this is just going to stay up the whole time. It's also in the lecture notes. So this is a plot of temperature on the y-axis. All the temperatures, pretty much all the temperatures I'm going to quote you are in EV, so energy units. If you don't know EV, that's 10 to the 4 Kelvin is about an EV. And on the x-axis, this is density in astronomers' units, which are inverse centimeter cubed, just so you can get big numbers involved. And there's just a smattering of what are considered plasmas on the board. Right? So there's a dividing line roughly between what's ionized and neutral, which is temperature specific. And above this line are things that are associated with the sun, like the solar corona, something called the solar wind, which is about 10 to the minus 14 solar masses per year, just evaporating off the sun and filling the interplanetary medium. Center of the sun, some fusion experiments. If there were a nuclear reactor to do nuclear fusion, it would live up there at the middle center where it says reactor. There's also the interstellar medium, which is in the lower left there, ISM. It covers a wide range of temperatures and densities. And above that, so the thing in the middle, Sagittarius star, that's the galactic center, which is quite hot and diffuse. And even more dilute than that is the intracluster medium. So this is, again, I'm going to take a poll. Who's familiar with the intracluster medium? Otherwise, I'll say something about it. Good. I'll say something about it. So galaxies tend to come in groups, and they're collected inside of a dark matter, a potential, gravitational potential, which is set by dark matter something like 10 to the 14 to 10 to the 15 solar masses within a megaparsec. And so these are the largest gravitationally bound objects in the universe. Most of the mass is dark matter, but up to about 20% of that mass is in the form of X-ray emitting plasma, which is just emitting from Bremsstrahlung radiation. And that's where it lives. So it's about a keV to 10 keV, so 10 to the 7, 10 to the 8 degrees Kelvin. And it's very dilute. The number density is like 1 part in 1,000, 1 part in 100, in that range. It's a really fascinating plasma for reasons that I'll get to later. But anyway, that's where it lives on that board. And then there's this diagonal line that I've drawn. And that brings us to the second part of the definition of a plasma. So sufficiently ionized, which I said is actually difficult to precisely define. It's system specific. And then the second part of the definition was something involving collective phenomena. And collective phenomena mathematically is diagnosed by this thing, lambda here, which is, I've written in here for those of you who might recognize what this is, but this is lambda d, so it's the Debye length. And so this is the number of particles in a Debye sphere. And the idea is that if you have just an isolated charge, suppose I have an isolated proton, it's going to attract a swarm of electrons around it, which are trying to shield that potential. And you don't have a Coulomb potential anymore. You've got a Coulomb potential which is exponentially attenuated because it's being surrounded by oppositely charged particles. And this is the number of particles in that sphere where the Coulomb potential has been exponentially attenuated by all these charges. And so this is a bit of a dividing line between what we traditionally think of as a plasma, which is everything to the left of this line, and things that we traditionally think of metals, which don't have collective behavior, where the Coulomb potential is really important, where binary interactions between individual particles are the dominant physics, which is driving the evolution of the system. When you have many, many particles per Debye sphere, instead you have collective interactions amongst, in some cases, this could be like 10 to the 20 big. Like, I think in the intracluster medium, this number is like 10 to the 25 or something like that. So 10 to the 25 particles are interacting together to produce electrostatic fields, which are just moving the particles around and trying to screen the Coulomb potential. And what this means is that the majority of the particles are not interacting. They are interacting as binary pairs, but that's very rare. For the most part, they're interacting via electrostatic interactions, which have been set up by all of these lambda particles inside of a single Debye cloud. And so that's what I mean by collective interactions. You're not really thinking of individual particles like doing billiard ball mechanics, right? It's really particles moving through a plasma, sending out electrostatic waves, and those waves talking to all the other particles in the plasma. And so, what is a plasma? It's a sufficiently ionized, whatever that means. But in terms of astrophysical plasmas, it's really stuff that lives to the left of this line. Of course, there's things, white dwarfs here. They're kind of in between. There's a whole division of, quote, plasma physics, which is not to the left of this line, called strongly coupled plasmas, even though we usually think of a plasma as weakly coupled. So again, you might see different semantics in different places, different definitions. That's why it's hard. That's one reason that I just put a whole bunch of astrophysical plasmas on the board. So you could just sort of get the lay of the land. Good. So on this board, I've been a bit more quantitative. I've just picked a few from here. So the solar wind, so the particles which are gravitationally unbound from the sun and just streaming into the interplanetary environment. So I've given temperatures, densities, and magnetic field strengths of the system evaluated at 1 AU. So where the Earth sits, you put out a spacecraft that has a magnetometer on it. You measure magnetic fields. You got a Faraday cup on this thing. It counts particles. You got the full distribution function of all the particles just by putting a spacecraft up into the plasma and just counting. And from that, you can get things like the temperature, which is about 10 eV. It's 10 to the 5 Kelvin, roughly. Number density is about 10 particles per cubic centimeter, and a magnetic field strength, which is about 100 microgauss. I already mentioned the intracluster medium, so the plasma that sits in galaxy clusters. It's just from gravitational energy is heated up to very hot temperatures. Typical temperature at about 100 kiloparsecs away from the center of a galaxy cluster. Remember, for context, I said that a galaxy cluster is about a megaparsec. A typical galaxy is about 10 or 20 kiloparsecs. So this is bigger than an individual galaxy, but not as big as the entire cluster. So this is a typical temperature gradient length scale in a cluster. So on this typical sort of macro scale for the plasma, the temperature is something like 1 to 10 keV, so 10 to the 7 degrees and up. It's really diffuse, so 5 times 10 to the minus 3 particles per cubic centimeter. Magnetic field strength we know from some Faraday rotation maps, if you know what that means, and also some synchrotron emission. And it's about a microgauss, just like everything else in the universe, apparently, except for compact objects, which is the rest of the school. So a bit closer to home, well, not really. If you go in our galaxy, closer to home, but then you go to the galactic center. And you go within 0.1 parsec of the galactic center. There's a 4 million solar mass black hole, which has captured you. So this is the Bondi radius, for those of you who know what the Bondi radius is. For those of you who don't, it's approximately where the escape speed of that 4 million solar mass black hole is the sound speed. So if you're sort of sonic, this is where you're marginally bound, roughly. The event horizon is much, much smaller than this, right? So here the temperature, it's like a keV. Number density is 100 per cubic centimeter, and the magnetic field is about a milligauss. As you go even closer to the black hole at the galactic center, of course, the temperature goes up, just because there's more gravitational potential energy that you've liberated. The number density goes up. We don't know really much about the magnetic field there. Before I say anything about the interstellar medium, these three systems have something in common, which is something I'll come to later, which is that they're just barely a fluid. So I'm going to be talking about MHD, which is the description of a conducting fluid subject to Lorentz forces by a magnetic field. But you can't apply it rigorously here. You can apply it rigorously here only on the largest scales. Even then, it's not great. And you can't apply it rigorously here. But there is a reason to still talk about MHD, not just from a pedagogical point of view. Yeah, if you understand MHD, you can move on to more sophisticated things. But also, even though people know you can't apply MHD to these systems, they still do. And so there's two reasons to learn it. One is that so you can understand why people can get away with that. MHD, even though it has its assumptions that we'll go through, it's remarkably applicable. Like you can still use it in a lot of systems where it's not formally accurate and still get decent answers, which are within an order of magnitude at least of the actual answer that you would get from a more detailed treatment. It's also worth going through because then you'll know where MHD breaks down for these systems. Interstellar medium, the warm phase, interstellar medium comes in a variety of phases. I'm not going to talk about those phases. I'll just talk about the warm phase. Some aspects of the cold phase will be relevant to topics that I'll get to at the very end of the lecture, and also things that are similar to what Phil will be talking about. But the temperature, the nice thing about the interstellar medium is everything is 1. So the temperature is an EV, the number of density is 1 per cubic centimeter, and the magnetic field strength, I wrote 5, but just 5 is 1 to an astronomer, right? And so that's really easy. What makes the ISM really difficult is that if I asked you what the equivalent temperature involved with the magnetic energy is, it's also 1. Same for cosmic rays, same for gravitational potential. Everything is in equipartition at about 1 eV per cubic, 1 eV, right, 1 eV per cubic centimeter. And that makes studying the interstellar medium really difficult because you have a whole bunch of physics which is equally important all working at the same time. But as opposed to these other systems, the majority of the ISM is squarely MHD. So that's a good application of what I'll talk about. So we've got these parameters. And I said, back when we were thinking about what is a plasma, it's sufficiently ionized. It exhibits collective behavior. Clearly, plasmas that satisfy this criteria are still varied. And so you need some more dimensionless parameters to define your system. And so I thought I'd go through some of these dimensionless parameters. And like I said at the beginning, some comparison of length scales in the systems. The first dimensionless parameter I want to talk about is the plasma beta, which is just the thermal pressure of the gas divided by the magnetic pressure associated with the magnetic field. And this is also a ratio of two velocities, which are really important. So this thermal velocity here, it's just, if you had some sort of Gaussian distribution of particles, it's roughly the standard deviation of the random velocities of the particles in your plasma. And then there's VA. Which is called the Alfvén speed. And we'll get to this. This is, if you don't know this, this is the velocity at which magnetic disturbances in the plasma propagate. It's just the characteristic velocity of a magnetic disturbance as it propagates in a plasma. So by comparing these ratios, you're saying something about, you're saying something about a lot of things. You're saying something about maybe the comparison of speeds of different waves, like if I send a sound wave into the plasma versus an Alfvén wave into the plasma. The size of beta tells you which one of these waves might play a role in the dynamics, an important role in the dynamics. The plasma beta might also say something about whether the magnetic field is important for confinement. Like in terrestrial plasmas, the plasma beta is really, really low, because the idea is that you want to confine a plasma using a magnetic field. It's really hot, so you have to compensate for that energy density, which is in the hot terrestrial plasma, by putting it in a really, really strong magnetic cage. And so you have a very low plasma beta in a lot of terrestrial plasmas. In astrophysics, you don't have to rely on the magnetic field to confine the system because you have gravity. So in astrophysical systems, as opposed to terrestrial systems, the plasma beta is generally large, with the exception of like the solar corona and things like that. But for the most part, plasma beta in the interstellar medium is just like everything else, order 1. So that's nice. The plasma beta in the intracluster medium is something like 100 or 1,000. So the magnetic field is energetically not important compared to the thermal energy. In the solar wind, the plasma beta around 1 AU is roughly 1. We think near the galactic center that the plasma beta is roughly 10. So yeah, so that's plasma beta. I've got these numbers in the notes, so you don't have to scribble them down as I'm telling you what they are. Good. And in the notes, I've also compared these astrophysical systems to numbers that are relevant to terrestrial magnetic fusion, magnetically confined fusion experiments. So there's one called JET, which is a joint European torus operated in the UK. And it's just nice to see some of those numbers. You might not be familiar with those numbers if you're interested in astrophysics, but it's really a stark comparison between an astrophysical environment where the plasma beta is generally 1 or bigger and a terrestrial plasma where the plasma beta is 1% instead of 1. Good. So that's one parameter. The next thing, which is often looked at is the mean free path. So this is V thermal over some kind of collision frequency. And this is where this is what's telling you whether the rest of this lecture is meaningful or not, right? So this by itself isn't telling you that, but this is going to tell you something really important if you compare it to other characteristic scales in the problem, right? So a fluid is characterized, if I call something a fluid, that means that the mean free path is much smaller than any length scale that I'm interested in. So that kind of makes intuitive sense. Water is a fluid. It's very collisional. Mathematically, why this is important is because this guarantees that you can write the distribution function like that. So in MHD, and we'll come to this again, the distribution of the function of the particles, so the number of particles with a given velocity in a given region of space. In MHD, this is Maxwellian. Right? And it's the smallness of the mean free path which is what guarantees that. You can do this rigorously via something called a Chapman-Enskog expansion. I'm not going to do any of that stuff, but I wanted to give you those words so you know that they exist. In the notes, I've given you some different types of collision timescales. Some are for fully ionized plasmas, where this is just set by Coulomb interactions between, they're Coulomb interactions which have been attenuated on a Debye length. I've given you expressions for that. I've also given you expressions for collisional timescales in poorly ionized plasmas, like where stars form in molecular clouds or protoplanetary disks. So those are in the notes. So this determines whether it's a fluid, but it doesn't determine whether it's a magnetized fluid or not. Right? And that involves something that I'll denote by rho, which is V thermal divided by the cyclotron frequency. So this thing here is, just QB over MC. Right? So it's the characteristic frequency of a particle gyrating around a magnetic field. And if you want to know whether the system is magnetized, you also have to make a comparison between this Larmor scale, the sort of turbulent scales, or whatever other scales that you're trying to describe with MHD. So you make this comparison, and then you also make this comparison between the Larmor scale and the mean free path. MHD formally has 0 mean free path. And that's what guarantees every single fluid element that you're looking at to be a local Maxwellian, to host a local Maxwellian of particles. MHD formally has 0 Larmor radius. So in MHD, you're not concerned with the fact that the particles are gyrating around a magnetic field. They're not. They're just points, which are just moving along magnetic field lines. And in ideal MHD, not moving across magnetic field lines. And we'll get to that. I've also given you specific numbers for I think, the ion Larmor radius. You can see from the definition of V thermal and the gyro frequency that the electron Larmor radius is a factor of a square root mass ratio smaller. So in hydrogen, the electron Larmor radius is 1/42, 1/42 times the Larmor radius of an ion. I'm not going to write the numbers on the board. You have them in the notes. But what I will say is that in all of those systems that I put on the board, this is tiny. So to give you an extreme example, in the intracluster medium, so the outer scale of the turbulence is something like 100 kiloparsec. Remember, a galaxy is something like 10 kiloparsec. This is 10 to the minus 9 parsecs. So those are, if you have no concept of what that is, those are drivable distances. It's like, you can drive that. Maybe cross Russia a few times. and that's a Larmor radius. It's still huge, right? But it's tiny compared to the macroscopic scales of interest. In the solar wind, this is about 6 orders of magnitude smaller than an AU. So it's 10 to the minus 6 AU. So these are very, very magnetized plasmas. Why they might not be MHD is because of this. So the mean free path in the solar wind is 1 AU. So statistically, some particle leaves the solar corona, and statistically it's undergone a 90-degree deflection in its trajectory once by the time it reaches the Earth. So that's not a fluid, right? Intracluster medium, the mean free path is something like a kiloparsec. So it's sort of galactic scale, which is pretty big. So that's not necessarily much, much smaller than the things you're interested in if the outer scale is only 10 times bigger than the mean free path, right? ISM, the mean free path is very small in the warm phase. So that's very much an MHD fluid. It's not an ideal MHD fluid, but it's close to it's very close to an ideal MHD fluid. I give you those numbers in there. Right, so there's one more thing I want to say. It's kind of out of order from the notes. But what I'm trying to build towards is ideal MHD, right? And ideal MHD is for a plasma whose plasma parameter is infinite, whose mean free path is 0, whose ion Larmor radius is 0, whose plasma beta is just order 1. And by order 1, I don't mean 1. I mean it's not 10 to the 20. It's not 10 to the minus 20. It's 100 or 1% or 1,000 or something like that. But I haven't said anything yet about being conducting, which is what an ideal MHD plasma has to be, is perfectly conducting. And that involves something called the magnetic Reynolds number, which is this. So you take some characteristic velocity that you're interested in. In a lot of MHD systems, this is just like the Alfvén speed, or maybe some characteristic turbulent speed in the system. You take some length scale that you're interested in, and you divide by the resistivity of the plasma. So this is it's a magnetic diffusivity. So this is a dimensionless quantity. This is a diffusion coefficient right here. And 1 over this is the conductivity of the gas. So it tells you the Reynolds number in every single system over there is huge. So now we'll get on to the MHD equations, now that we've focused on what we're going to do. And then I'll show you some just basic theorems that come out of the MHD equations, and then we're going to break the MHD equations. MHD equations you can derive 2 ways. Usually the first time people see these equations, they're written down, just here they are, right? And you can motivate them physically, and that's what I'll do. The rigorous way of seeing these is actually writing down an equation, a kinetic equation, which tells you how the particles evolve in the system, and you take moments of these equations. And I might mention that a bit later in my second lecture. They're also done, that procedure is also done step by step in the notes. So you have something to fall back on. But how this starts is, so first MHD equation is completely obvious. And it's just this. So this row here, this is mass density. Sorry, I also use rho for Larmor radius, but it's usually obvious in the context because in MHD there's no Larmor radius. So you'll never see rho in MHD equations, so it's fine. So this is mass density in this case. This is a fluid velocity, and I'm going to come back to that. Because even people that say they know MHD actually screw up when you ask them what U is. It's a bit subtle. And this is something called the continuity equation, which is just expressing mass conservation. Right? So here's a quantity which is being conserved, and this is the flux of that quantity. And you can see if I integrate this over some volume, if I have some fluid element here, it's got some volume, and coming into it is some amount of mass density times the velocity, and flowing out of it is some kind of mass density times the velocity. And if I just ask how much mass is flowing in and out of this surface, this equation just tells me the answer, right? So if I integrate this over volume, the volume integral of mass density is just mass. And if I integrate this over volume by a divergence theorem, I could just write this as an integral of this flow through a surface of that volume. So stuff that's flowing in and out, it's just bookkeeping, right? Stuff that flows in and out, and you get mass, how mass evolves. So it's intuitively obvious. It's just something that you can write down. Like I said, you could rigorously obtain it by something more general, which is phase space conservation, by taking a moment of that equation. That's done in the notes. I think a bit of foreshadowing. Note that I've said nothing about the composition of my plasma. Right? I didn't say whether it was neutral, whether it was ions, whether it was electrons, whether it were dust grains or anything. Right? This is just mass conservation. I could append a species label to any one of these things, and it would still pretty much hold. But this, as written, is for all the things that are in a fluid element taken as a whole. So it's the total mass inside of a fluid element of some volume. So the next thing is you could write a variety of ways. I'm going to write it like this. Right, so this is just F equals ma. So here's m, right? So there's my mass density. This is A. But it's A in a subtle way. If you're not used to, if you're not very familiar with fluid dynamics, you need to measure this acceleration in a particular frame. And it's the frame moving with the fluid element. So this is the time rate of change of the velocity. But this piece right here, this u dot grad, is what tells you to measure that rate of change in the frame of the fluid element. So this thing is called, might be called a Lagrangian derivative because it's in a Lagrangian framework, which is a co-moving frame. Sometimes you hear it called a convective derivative because what this operator does is it convects something. So it's convecting this time derivative with the fluid element, so you know to measure the time rate of change in a certain frame. And then on the right-hand side, there's whatever forces you want. So here's a Lorentz force, J cross B. I think you'll get some lessons in relativistic MHD later, but everything I want to say is non-relativistic, which means that Maxwell never existed. And we just have amp here, right? So just J is curl of B, full stop. So there's the Lorentz force. Remember, ideal MHD, it's a perfectly conducting plasma. So that plasma experiences Lorentz force because it's charged. The currents are sustained by the movements of the charges in the plasma. But MHD is completely agnostic about that, right? You know nothing about the individual motions of charges. All you know is that those charges adjust their velocities so that the current associated with that is curl of B. And that's instantaneous, right? There's no time derivatives here. So if the magnetic field adjusts to have a curl, the currents instantaneously, like the ions, the electrons instantaneously adjust themselves, and vice versa. It goes both ways. So pressure gradient is just standard hydrodynamics and fluids. If the pressure is different here and here, there's a force associated with the force per unit area from the pressure pushing in different directions. One thing that's worth noting is that this is minus grad of a scalar. And this goes back to the thing that I erased right here, which is that in MHD, the distribution function is Maxwellian. So as far as the random motions of the particles in this plasma are concerned, there's no special directions. So up is the same as this way, is the same as, everything is isotropic as far as the random motions of the particles go. Mathematically, that just means that its pressure is a scalar. In general, this pressure is a tensor. And we'll come back to that probably in the second lecture. Right, so the fact that this is grad of a scalar goes back to the assumption in MHD that the mean free path is formally 0. And yeah, if there's any finite mean free path, you're not guaranteed this. So these are two equations that once you know how to just do some vector calculus to a moving frame, these are also intuitively obvious, just F equals ma, right? But it's just in a moving frame. I'm not going to do it right now, but there's obviously a vector identity associated with curl of B cross B, and I want to talk about that in a second. Right, so you have two equations. Well, you've got 4 equations here, one for each component of the velocity. So 3, 4, but there's 5 variables because, well, you don't know how to evolve B yet. So it's actually more than that, variables. You don't know how to evolve B yet, and I haven't said anything about how the pressure evolves. Now this is a bit subtle. I'm going to write down an equation for the pressure, but believe it or not, you don't always need it to solve these equations, and I'll show you why. So the next equation I'll write like this. So you can write this in a variety of forms. I like it this way because it's also intuitively obvious. This is the entropy. It's the hydrodynamic entropy. It's log of the number of states. So it's P over rho to the gamma. Gamma is some adiabatic index. So ratio of specific heats. 5/3. Doesn't have to be 5/3, but it's 5/3 here. And so entropy ought to be conserved in a moving fluid element. So that's what the big d by dt is. Its time rate of change is 0 in a moving fluid element. One could obviously append whatever you want to the right-hand side. Plasmas, they radiate. They can get heated by various processes. There's heat conduction, so heat can go from A to B and vice versa. All of that is not an ideal MHD, at least the simplest form of ideal MHD. You just conserve entropy in fluid elements. And why do you conserve entropy? Well, the distribution function is always Maxwellian, right? So you're always sitting at the lowest, I mean at the highest entropy state. So I made a comment about sometimes you might not actually need this. And sometimes people, they make an assumption of incompressibility. So the fluid flow has no divergence. And in that case, you don't use this equation. Basically, the pressure, it's an overconstrained set of equations. And the fact that you've imposed incompressibility tells you what the pressure needs to be in order for the system to be incompressible. So if that didn't mean anything to you, fine. Just keep in the back of your head that if somebody gives you an incompressible plasma, you shouldn't use this. This overconstrains the problem. Good. And in the notes, I say a bit more about this stuff, but I don't want to do that right now. In the notes, I also say something a bit more about this u dot grad u, this vective piece of the time rate of change. It can get a little tricky in curvilinear coordinates because you're taking a derivative of a vector quantity. If you remember, like if you, in cylindrical coordinates, say the derivative of a unit vector is not necessarily 0, right? Or in spherical. And so it can get a bit tricky. You get a bunch of additional terms. I talk about that in the notes, and it's kind of reinforced in the first problem of the first homework, where you talk about MHD equations in like in an accretion disk, in a rotating frame. I won't say anything about that here. Good. So then we're almost done. We just need an equation for the magnetic field. And what do we know about electromagnetism? We know like Lenz's law. If there's a curl in my electric field, I produce a magnetic field, and vice versa. The problem, though, is I've said nothing about electric fields here. Right. And some of you who don't know anything about MHD may be thinking, well, I learned in E&M that the divergence of E is just charge density, and I'll just solve that. That doesn't work in ideal MHD. And I'd just like to spend a few minutes talking about why that doesn't work. So this electric field, which is associated with Poisson's equation, is not this electric field. I mean, it kind of is, but it's not. So the reason, first of all, the reason why this doesn't work is that in ideal MHD, the total charge density in a fluid element is 0. It's not, in ideal MHD, it's formally 0. In reality, it's not. But there's a series of assumptions that go into MHD, and the assumption is that the total charge density in any fluid element is exactly 0. Which says that in ideal MHD, this would imply that you've got a constant electric field. Well, constant electric field, it's not going to have a curl. The magnetic field's not going to evolve. This just doesn't work. Right? So I wanted to pick this apart a little bit. So it's not exactly 0. And it goes back to this plasma parameter and the fact that there's a large number of particles per Debye sphere. And it also goes back to a hidden assumption along the way that I'm considering non-relativistic species. So there's two things that go into this. But the most important one is that the length scales that you're interested in the problem are much, much bigger than the Debye length. And what this means physically is that any volume that I take in this plasma, which contains lambda number of particles, there must be many of those inside of that Debye volume. And that Debye volume must be much, much, much smaller than any length scale that I'm interested in. And what this means is that on the scale of the fluid elements that I'm evolving, there's roughly equal amounts of ions and electrons in that volume. So this is called quasi-neutrality. It's not exact neutrality. It's quasi, because there's actually a time scale argument that goes into this, and a length scale argument. You're saying that the plasma is not exactly neutral, but on the scales that we're interested in, it acts as if it were a neutral fluid. Equivalently, you can say that the time scales that we're interested in are much, much longer than the time scale on which Debye clouds are set up. So much, much longer than the time scale on which the particles rearrange themselves to screen Coulomb interactions and give this collective behavior. So what that all means is that we just can't rely on this equation. It's not part of the MHD equations. So that means we need to get our electric field from somewhere else. And that goes back to this thing that I have not erased. So in ideal MHD, this is formally infinite. And that says something about what the electric field has to be. If it's formally infinite, electric field is 0. But I'm going to put a prime here, because I don't actually mean the exact electric field, and I'll come back to that. What I mean by 0 is that when you think of Ohm's law, the currents in the plasma are related to the voltages through a resistivity. And this is saying the same thing. There's some currents, there's some voltage in the plasma, or like electric field, and this is equal to a resistivity times a current. In ideal MHD, there is no resistivity. This is formally infinite. So this is like Ohm's law, but without Ohm. It's just the law. OK, and then there's this prime. And this is not true. E equals 0 is not true in every frame. It's true in a special frame, which is the frame which has been boosted to the fluid frame. So if you measure the electric field in the fluid frame, and this is just how you transform electric fields, in that frame, it's perfectly conducting. And so now this tells you what the electric field has to be in Faraday's law. So all this ends up just giving you dB dt is curl of u cross b. And this is special enough that it's not really called Faraday's law. Sorry, Faraday. It's called induction equation for reasons that I'll tell you about in a second. So this closes the system, right? So now we know how to evolve the magnetic field based on the fluid velocity. That fluid is assumed to be infinitely conducting. It's assumed to be neutral or quasi-neutral. In what I've written, it's assumed to be non-relativistic. And it's assumed to have 0 mean free path. And there's no Larmor radius anywhere on the board, right? So the particles, they do gyrate. There's a magnetic field, there's a Lorentz force. The particles are gyrating around the magnetic field. But MHD, that's not in MHD. It's formally, the Larmor scale of the particles is formally 0. So everything's closed. But you could see the assumptions we made along the way, right? Very few astrophysical systems satisfy all these assumptions all at the same time. Like the warm phase of the interstellar medium does a pretty good job. So any questions about this? I imagine some of you, or about half of you, have seen this kind of thing before. Never hurts to do it again. But for those of you who have never seen this, I hope this wasn't too fast. If it was, consult the notes. Everything is given there in more detail. Just wanted to provide an overview. What I'm going to do is state some facts, which are proven in gory detail in the notes, because I want to get to something in particular. One is that this equation implies that the flux threading any fluid element is a constant. So if I have a blob, here's my fluid element with a volume V, and it's threaded by some kind of magnetic field. It's not obvious from this formula, but there's two ways of showing. One's called Alfvén's theorem, one's called Lundquist's theorem. They're both derived in the notes. But it says that as this fluid element moves around with some velocity, the magnetic field lines are advected with that. And they move such that the flux through any fluid element is a constant. That's not true in general, but it's absolutely true in ideal MHD. And there's two ways that you could prove this. You can prove it by saying that the field lines move with the fluid elements, and that gives you something called Lundquist's theorem, which is proven in the notes. Or you can do a volumetric thing and say there's some volume. I can calculate the flux through this volume. If I move that volume, does the flux change? And that's Alfvén's theorem. And that's proven in the notes. It's fairly straightforward. It's just vector calculus and some identities, that's all. Right, so in the time remaining, I want to say something about waves and something about breaking this, which is a lot for 20 minutes, but I'll do my best. Good. So we have this set of equations, two of which I just erased. Wish I didn't. And usually the first thing you do in MHD, or really in any problem in astrophysics, I would say, is you should do some sort of linear theory. What do I mean by linear theory? I mean, consider a plasma which, yeah, I'll follow his instruction. Let's consider some plasma which is characterized by some state. There's some background density, rho naught. There's some background pressure, some background magnetic field, some background fluid flow. And I consider small changes to these quantities. And what I mean by small and what I mean by linear theory is that all the terms, once I plug this decomposition into the equations, all the terms which are second order in this delta are just 0. And this gives you something called linear theory. And it's sort of the entryway into actually understanding the physics of the equations, because linear waves are very simple for the most part. And what I'm going to do for you right now is a problem where I just consider a static medium. And all these things here are constant. So it's just a constant static fluid, which is conducting. And I'm just going to put ripples into this fluid. And then just ask, all right, if I just took this fluid and I perturbed it with these little ripples, what's going to happen? And so what you do is you plug these into your MHD equations. Like I said, you drop all the second order terms in these fluctuating quantities. And you get something that looks like this. Guess that's all. So that's just linearized MHD. So all I've done is put those variables in, dropped all the second order terms, and that's all you're left with. I guess there's this equation, if you need it. Which is just adiabatic evolution. If gamma 1 is 1, it's just isothermal evolution. And just like you do in undergrad mechanics, this is just a matrix algebra problem, right? Everything is linear in all the variables that you're trying to solve for. So there's just a giant matrix multiplied by a column vector of delta u, delta rho, delta ux, delta uy, delta uz, delta p, delta b. And you just have to solve that. You know that the solutions look like this. So they're just plane waves. And they have some wave vector, 2 pi over some wavelength and then some direction. And there's some frequency, which in general is a complex frequency. So all you do is you plug this solution into the linearized equations. This is just a matrix problem. And you know that you have solutions if that matrix has 0 determinant. Right? So you just have some giant matrix dotted into delta rho, delta u, delta p, delta b is 0. You take that determinant, work your magic, and this gives you what's called a dispersion relation, right? Which is how the frequency depends on the wave vector. And so this whole procedure is done in the notes. And I'm just going to give you some solutions and talk about them physically. Right. So this is the dispersion relation you get. I've adorned the k vector with parallel and perp. This is parallel perp with respect to b naught. So this k parallel is just, just k along the background field direction, because that's the only direction in the problem. And so there's a k parallel, there's a k perp. And one nice thing about this is that you see that I've factored out a chunk. And this thing right here is what gives you so-called Alfvén waves. So I'll talk about that in a second. So what those, you notice, so one solution is just this bracket 0, and there's no k perp in here. Right? So any k perp that you have for this bracket, it doesn't matter. What they look like is just this. Just perturbed field lines like this. There's k in the direction of b naught, so there's only k parallel really matters for this. And you can see that they have a propagation speed, but that they only travel along the magnetic field because there's a parallel. Right? So the phase speed of this, no, that's sad. It's just plus or minus VA. So these magnetic disturbances just run up and down the field lines. And they have nothing to do with compressions in the plasma. If I completely screwed up delta P, I could still get this. One reason that MHD works so well, even in collisionless plasmas, is that Alfvén waves don't require collisions. They don't change, the distribution function is still Maxwellian. If you put a linear Alfvén wave in it, it doesn't change. So they're an incredibly robust property of a magnetized plasma, regardless of whether it's a collisional plasma or not. And then you have this bracket, which is all the stuff that really, really matters for the MHD approximation. These are all the things that come from things that compress the plasma. Nothing, I mean, the density here doesn't change from an Alfvén wave. Nothing changes except the magnetic field shakes up and down. And you have you just have velocities that just go up and down at the Alfvén speed times the amplitude of the wave. So those are really simple. These waves are called magnetosonic waves. So this is Alfvén. And then the other branch is magnetosonic. And they split into something which is called a slow mode and something that's called a fast mode. And you can tell that there's two of them because there's a w squared, there's a mega squared here, and there's a mega squared down here. So there's actually 4 roots to this equation. And in waves, usually 2 roots look exactly the same. They're just something going this way versus something going that way. But there's 2 sets of those. And those sets, that set of 2 can be split into something called slow and fast. And like I said, these are all derived in the notes in gory detail. Limits are taken. I'm just going to draw a picture so you know what these actually look like. Notice there's a k perp involved. So let's see. So suppose these are my deformed field lines. So that was the B0 direction, just like before, like this. But because there's a K perp, you have regions where the field lines are closer together and regions where they're further apart because they're just slightly oblique in their propagation direction. And whether it's fast or slow has to do with whether the pressure is high, where the magnetic field pressure is high, or if the thermal pressure is low, where the magnetic field pressure is high. So here, there's a high magnetic field because the field lines are closer together. Here, there's a low magnetic field because the field lines are further apart. And if it's a fast wave, if you also have high pressure in those regions, and it's a slow wave if you have low pressure. So this is fast, this is slow. And it's just a matter of whether the two forces in your problem are acting in concert or not. Right? You can imagine if two forces are acting in concert, of course the wave would be faster because there's two forces which are driving the wave. So that's where this comes in. So this gets back to what exactly the Lorentz force looks like. There's two pieces associated with the Lorentz force. One just enters this type of fluctuation. And that's just magnetic field lines have tension. Like a string, you pluck them, and they just send a wave, just like a string. The Alfvén speed is nothing but it's just related to the tension in the string and the mass density, which is loaded onto the string, just like in basic mechanics. This tension's involved, of course. I've bent the field lines. But it's also, there's magnetic pressure, which is also involved. And that's here. So this is pressure. The fact that I've taken some field lines, I've pushed them closer together, and field lines don't want to be brought closer together. They want to just, the perfect state is if all the magnetic fields are equally spaced and just straight. Here the field lines are equally spaced, but they're not straight. Here they're both not equally spaced and not straight. So this is the full Lorentz force. This is just one piece of Lorentz force that acts. OK. And I have 10. OK. No, this is, I think this is about where I wanted to be. OK. OK, yeah. So now I just want to have a discussion about why in your research career you'll pretty much never use this. Why it's good to know. It's the foundation of everything that you'll use. It's a very good framework to do some simple calculations in. But modern astrophysics is moved beyond this, right? So the cutting edge frontier astrophysics work is not about these equations. It's about things that are breaking these equations, things that break the equations but don't actually give you a substitute for what they should be. And it's all about figuring out what that substitute should be. So I thought I'd just have a brief discussion about one important way that this will break down. This will lead into the next talk. I made this comment at the beginning about this velocity. And I just said it's a fluid velocity. I said, don't worry about it. It's just a fluid velocity. Now, if you derive these equations from the Vlasov equation rigorously by taking moments of a kinetic equation, what you'll find is that this u is the center of mass velocity. So if I sum up all the masses of all my species times all their densities times all their fluid flows, I divide by the total mass. It's the center of mass velocity. Formally, this u in MHD is the center of mass velocity. And you can see that you'll instantly get in trouble there because let's go back to one of the examples I said at the beginning, which is like a protoplanetary disk or where stars form. I said the degree of ionization, so the number of ions versus the number of neutrals in a molecular cloud where stars form is something like 10⁻⁷, 10⁻⁷ 10 minus 6, 10 minus 8, something like that. So that means the center of mass velocity is the neutrals. Well, this says that flux is frozen into the neutrals, right? Which makes sense. I mean, why should a neutral gas, predominantly neutral gas, know that there's a magnetic field? I mean, so right away you see that these can start breaking down, and you have to be really cognizant of what you mean when you write down rho, when you write down u. In these equations, formally, there's actually a term missing. There's another term missing that I dropped, which is that suppose I have a gas where there's electrons, some ionized hydrogen, and also some ionized helium. So two types of ions. There's a term here that I dropped that has to do with the differential motion between the ionized hydrogen and the ionized helium. All these things are categorized in the notes, and I'm just saying these quickly, but you can read about them in the notes. So it's really important to notice this. Formally, what's going on is that usually the flux is almost frozen into the electrons. But the electrons have very, very little mass density, so they're not actually contributing much at all to this U. So this U and this U are not the same. In ideal MHD, they're the same because everything is co-moving. Like everything in the fluid element is just moving the same. There's a little bit of residual motion between the ions and electrons because you need a current. But as far as the macroscale dynamics, there's no difference between the ion motion, the electron motion, and if there's neutrals, the neutral motion. And so what that means is if you actually care about the difference between what's going on in some neutral part of your gas versus the ionized part of your gas versus the electron part of your gas, you're not allowed to write down a set of single fluid equations for the entire plasma. You need to write down an equation for your electrons. They have a continuity equation. There's a force equation for your electrons. For the ions, there's a continuity equation. There's a force equation for your ions. If you have neutral species, there's a continuity equation for the neutrals. There's a force equation for the neutrals. And then you have an induction equation. And the only thing that you're guaranteed that the induction equation is actually frozen into is just the velocity of the field lines. Right? Magnetic field's frozen into itself. But this is not necessarily the electron velocity. It's not necessarily the ion velocity. It's not necessarily the neutral velocity. And all of those things make this induction equation complicated. Because you can imagine having a gas wiggling the magnetic field, and if there's a bunch of neutrals in that gas, how they know that I wiggled the magnetic field? They're not doing Larmor motion or anything. The only way that they can know that I wiggled the magnetic field is because those neutrals are colliding with the charges that do know about the magnetic field. So you have a whole bunch of charges which happily go, yay, there's a magnetic field. And then the only way the neutrals know is just because they're colliding with the ions. And so then you have to know, am I shaking this faster than the neutrals can know through collisions? And so I just want to close by telling you something about how that changes at least Alfvén waves, and how that process affects all the other waves. It's just done in the notes in gory detail if it's something you want to go through. Like I said, I didn't plan to get through everything in the notes, but that's why there's notes. So you could take it away with you, and if there's something in there that you want to learn that you don't know, you could work through. So I just want to come back over here to this Alfvén wave and just show you what happens in one particular case. So suppose I have some ions in my gas. They have some fluid flow. I have some electrons in my gas. They're not exactly moving the same, or else there wouldn't be currents. But the difference is not so great. And then suppose there's also some neutrals. Right? And they're probably not moving the same way because there's different forces on them. These guys see the Lorentz force. This guy doesn't. They both see collisions back and forth amongst all the different species. So what would happen to this Alfvén wave? Well, you'd send it in. I'd have some electron here, which would see the magnetic field move. And, electrons are trying to gyrate around the magnetic field, so they see that the magnetic field moves, and so they move with it. And the neutrals just don't. But now there's a neutral here, and there's an electron up here, because these electrons have moved with the magnetic field line. And the only reason that this neutral is going to move is because it collides with this electron. And there's a momentum exchange. Same with the ion. There's some momentum exchange between them. And that's what just pulls along the neutrals with it. And so instead of just having an equation like this for your Alfvén waves, you need to account somehow for that difference between an Alfvén timescale, which is associated with this, and the collision timescale when that momentum exchange occurs. And what you get, I'm going to screw up the sign, I think. Let me check the sign. I think that's fine. Yep. So you have this extra term in the middle. And this gives you damping. If you just solve this quadratic, it's just a quadratic, but there's an I right there. This is going to give you damping. And you can see what would make the damping really bad. So this is a time scale for a neutral to collide with an ion. In ideal MHD, this time scale is, wait a second, I did it the wrong way. This is not the right units. Inverse. There's a frequency down here. Yeah, okay. In ideal MHD, this time scale is 0, right? The neutrals are perfectly coupled to the ions. Sorry. Wait. Yeah, that's right. Yeah. Inverses screwed me up. So this term is not there, right? You can go to the opposite limit, where this is infinity, right? Where'd the wave go? You just have omega equals 0 in that limit. And you can see that there's a comparison between something involved with the speed of propagation of an Alfvén wave, or a time scale associated with that. So the time that it takes an Alfvén wave to cross some length scale associated with that wave, and a time scale for those neutrals to be informed about that wave, because the ions are moving, but the neutrals aren't. They have to be informed over some time scale, which is associated with that momentum exchange. And this is something called ambipolar diffusion. And you can see just by comparing things that there's a length scale below which the neutrals aren't going to respond. Basically, the Alfvén wave propagates so fast on those time scales that you don't have enough time for the momentum exchange to happen. So that's just one example. There's many examples in the notes, something called the Hall effect, some ohmic dissipation if the currents aren't perfect, ambipolar diffusion. I work through the dispersion, the full dispersion relation for these, and talk about it physically. You can read about it if you'd like. I'm done. Thank you.